Alrighty, so this video we're going to discuss Ohm's law, which is the fundamental equation, the fundamental way of analyzing circuits. It's the basic thing, it's the thing upon which most everything else is based, but it's important and it'll work for a great many circuits we're going to deal with. Of course, in order to do it, we need to understand how circuit analysis is going to work. Obviously, if you've ever seen electronic circuits, they look very complicated. And a lot of times they're very, very tiny, and it's hard to see everything. It's hard to see what's connected to what. So, what we do in general when we discuss circuits or when we devise a circuit we'd like to create, we don't draw it out or model it the way the circuit actually looks, but rather we create a picture or a diagram, which is a simplified version that more directly shows how things are connected. And so a typical circuit diagram can look something like this. That's a circuit. And, well, this is a circuit diagram, which represents a circuit. And it is drawings like this which we're going to analyze in this course. Now, in order to do it, we need to understand what are all the symbols. What are all the symbols that are in these diagrams? What do they represent? So, basically, we're going to have two main symbols for now. And as we progress through the semester, we're going to gain new symbols to add to our circuits for more complicated things. The first thing is this symbol here, which is a voltage source. Or a battery. Now, how it's drawn is a small line and a longer line on top of each other. Or, of course, we could draw it this way too, sideways. And so that's a battery. Or, you could think of it like the wall socket where the power is coming from, or a battery pack, or an adapter, or whatever, where the power, where the voltage starts, where the current is coming from. That's the voltage source. These lines that come off of the little sandwich-looking thing, that's just wire. Okay, but the actual voltage source itself is this part of it right here. Now, there is a standard for the directionality of which way the current flows through a voltage source. And unfortunately, it's a very confusing standard. And in fact, it's a standard that's not really standard because some people go the other way with it. But the way we're going to do it in this class is when we see a voltage source like this, we're going to assume the current goes from the small to the large side. Okay, so for instance, in this circuit diagram over here, I'm going to assume the current flows this way, clockwise. So from the small to the large. That's the standard we're going to use. It's confusing because there's the difference in which way the current is said to flow in a circuit versus which way the actual electrons flow in the wire. Unfortunately, way back when electricity was first being discovered, it was assumed that a current, electricity flowing through a wire or something, is a bunch of protons moving through the wire, positive charges. And so when they defined the direction of the current, It was defined to be the direction in which positive charges are flowing. However, it was later discovered that a current is not a bunch of positive charges flowing through a wire. It's actually electrons which flow through a wire. And so when you have the current said to be flowing one way, the real physical version is the electrons are flowing the opposite direction. And so it becomes a confusing thing when you say the current flows clockwise, but if you actually investigate and look in the wire and see which way electrons are moving, they're actually moving counterclockwise. We're not going to worry so much about it. Just know that this is true, that the direction of the current is opposite to the actual physical motion of the charges. And it's purely because Ben Franklin assumed one thing, which was a wrong assumption when he discovered electricity, and we decided as a community not to change it. We just left the designation for current the way it was, even though it's wrong, and we just accept it. So that's our first symbol, the voltage source. We assume the voltage source, what is it? It's a battery. It is that thing which pushes the electricity through your wires. That's how you can think of it, like a pump. You want to push these electrons through the wire to create the current, to let the power flow. Well, how do you do it? You use a voltage source. The voltage is like the potential difference between two places. And so if there's a high potential difference, then the charges really prefer to move from one to the other. And so it's like a really big pump, a strong pump pushing things through. If you have a very low potential difference, a low voltage, then they're only weakly wanting to go from one place to the other, so you have a very small current flowing. That's one way of thinking about a voltage source. The voltage source is that thing which pushes the electrons through the wire. Now the other symbol are these squiggly line looking things, which is this symbol here, or sideways it's like this, and these are called resistors. And these are things that you could place into your circuit, and all they do, just as their name implies, is they resist the flow of the electrons. They make it harder for the current to flow. Now, what are resistors? Well, it could be wire, a whole bunch of wire. Think about you're trying to push electrons through a material. If you have to push these electrons through a very long wire, there's a lot of material you have to go through. So it's like there's a lot of friction you have to overcome. So wires can act as resistors. You can have a light bulb. A light bulb is like a resistor. It's a fancy resistor. But when you try to push electrons through a light bulb, that light bulb is resisting the flow of the current. And of course, when it does this, it creates light, because the filament heats up because of all the friction and the interaction with the electrons flowing through the filament. And that heated filament, hot enough to send off energy in the form of light. So resistors, it could be a radio, it could be a TV, whatever it is, the symbol is a resistor. We don't worry about the specifics of what exactly the resistor is. It's just a resistor. So these are the two symbols that are going to compose our circuit diagram. Of course, they're connected by wire, which are the straight lines. And we basically will create all of the circuits for this course out of these symbols, like little toy models. Now, Ohm's law tells me the relationship, it gives the relationship between how much voltage and how much resistance is in the circuit and how much current can flow because of those two things. And the way it works is this. Ohm's law says, really easy, thankfully. Ohm's law says V, the amount of voltage in your circuit, is given by the current flowing through the circuit, I, times the total resistance of the circuit, R. Very easy. V is voltage, I is current, R is resistance. So the relationship is very straightforward. And a lot of times what we're going to do in this course, or at least what I'm going to ask of you, is I give you a circuit with some set of resistors and a voltage source. And I'll say, because of this voltage source and because of these resistors, what must be the current flowing through the circuit? And so it'll be your job to use Ohm's law to solve for the current. Or maybe I'll say, given this circuit, calculate how much power is produced by this circuit. And we'll see that equation later on. But it also has to do with voltage and current and resistance. Now we have an equation sitting here. We better talk about units. The units of voltage is, of course, volts, capital V. Volts. The unit of resistance is what's called an ohm, O-H-M. The symbol is a capital omega. It looks like a horseshoe. Oops. Greek letter omega, capital omega, which looks like a horseshoe. And that's ohm. And current, capital A, which stands for amps or amperes. So those are your units. Voltage comes in volts, current comes in amps, and resistance is in ohms. All right. So let's do a quick example. Here's a circuit. Let's say the voltage source is 10 volts. This is 5 ohms. In fact, let's do an easier one. And the question is, what is the total current flowing through the circuit? Well, not too bad. I use Ohm's law, V equals IR. I'm looking for current, so I want to find I, so this tells me I is V over R. The total voltage, 10 volts. The total resistance, 5 ohms. And I get an answer of 2 amps. Not too complicated, fairly basic. But of course, this is a very basic circuit. And the point of the course is going to be, can we take more complicated circuits and do a similar analysis? If we have a really complicated looking circuit, can I break it all down and figure out what kind of current will flow through? Now, how do we start going to more complicated, more complex circuits, more interesting circuits? Well, the first thing I can do is put an extra resistor. So what if instead of a single resistor in my circuit, as I had there, I have 2 resistors? Okay, let's say 10 volts. Let's let this be 8 ohms, and this is 2 ohms. How do I solve this problem? Well, now it's not as straightforward. Again, I want to use Ohm's law, and Ohm's law says V equals IR. So I want to use I as V over R. But what R do I use? There's two different R's in this problem. There's the 8 and there's the 2. And the question is, if I want the total resistance, how do I know what the total resistance of this circuit is? Well, I'm sure everybody right now is thinking, this is fairly obvious. If you have two resistors, all you got to do is add the resistance together and you get the total resistance. If one resistor is resisting by 8 and another one is resisting by 2, then the total resistance must be 8 plus 2 is 10. And of course that's true. In this case, we have a resistor 1, which is 8, and a resistor 2, which is 2. The total resistance should be 8 plus 2, which is 10. Once I know that, then I stick it into my equation. 10 volts over 10 is the total resistance to get 1 amp. And I would be correct. So that's nice. Thankfully, it wasn't more complicated. It was just straightforward. If I have multiple resistors, I add up all the resistors together and get the answer. What about this one? What if I have a circuit that looks like this? 10 volts, 8, and 2. And I want to go, again, what is the total current? Well, again, V equals IR, which tells me I is V over R. What do I have? I've got two resistors. I've got a resistor 1, which is 8, and a resistor 2, which is 2. And I want the total resistance. Well, obviously, 8 plus 2 is 10. I now know the total resistance is 10. And again, 10 over 10 is 1. And so the total current should be 1. But what if I were to tell you that the true current, I, the total current for this circuit, is actually 6.25. 6.25? What kind of answer is that? How do you get this? Well, this is where the rub comes in. It's not straightforward. It's not just if you have multiple resistors, you add up all the resistances, and it tells you the total resistance. That happened to work for the first circuit, but it doesn't work for the second, even though both resistors have a single voltage source of 10, one resistor of 8, and one resistor of 2. The difference is, how are those resistors connected to each other? If we look at the first circuit, the current, when it flows from this voltage source, it comes in, it's going to hit this first resistor and go through it, and then come out and then hit the second resistor and have to go through it as well, and then make its way all the way around. Okay? But let's look at what happens to the second one. For the second one, we've got the current coming in. It gets to this point here, and all of a sudden it has a choice. It could keep going to the right, in which case it'll hit the 2 and go through. Or the other thing it could do is go down instead and hit the 8. But then, either way it went, no matter what happens, it hits this point again and continues on, finishing the circuit. So notice with this second circuit, the fact that the current can choose which way it wants to go, it doesn't necessarily have to go through both. It could go through the 2, or it could go through the 8. In the first circuit, it had to go through the 8 and the 2 every single time. The second one, it only goes through one or the other. And so that's going to change how the circuit allows the current to flow. In the first case, that poor current has to go through all the resistors. In the second case, some of the current goes one way, some goes the other, but none of the current has to hit both. And so this is the difference between two main ways of connecting resistors. This first way is called series. When you have two resistors or multiple resistors all connected one right after the other, where the current has no choice but to go through each one of the resistors, that's called a series connection. The second is what's called parallel. A parallel connection is when two resistors are connected in such a way that the current can choose which way it wants to go. It does not have to go through both. Now, what's the difference? What's the main equation here? The main equation says this. If you want to know the total resistance for a series circuit, for a series system, then all you have to do is add up all the resistors together, which are connected in series. And that's what we did here. We had the 8 and we had the 2. They're connected in series. So we added 8 plus 2 to get the total resistance of 10. How do you do it in parallel? In parallel, the equation becomes 1 over the total resistance in parallel is 1 over R1 plus 1 over R2, and so on. So you don't add the resistors. What you add is the inverse of the resistors. And once you've added the inverses, you then have to take the inverse of that answer too. So, looking at our second example, we want the total resistance. 1 over the total resistance is 1 over 8 plus 1 over 2. 1 over 8 plus 1 over 2, well, if you want to add fractions, you have to get a common denominator. 1 over 2 is the same as 4 over 8. 4 over 8 plus 1 over 8 is 5 over 8. But notice, 5 over 8 is 1 over R parallel. You don't want 1 over R parallel. What you want is R parallel itself. So you take 5 over 8 and you take its reciprocal, which is 8 over 5. And now you have the total resistance, 8 over 5. Once I know 8 over 5, now I could use my Ohm's law thing here. 10 over 8 over 5, which is 50 over 8, which is hopefully 6.25. And so this is the main thing we're going to deal with for this lecture. Taking circuits, allowing these resistors in these circuits to be connected either series or parallel or some combination. Can we calculate the total resistance? Because if we can calculate the total resistance, then we can calculate the total current with Ohm's law. All right. Now, here's something you have to be very careful about. Parallel. Do not confuse parallel connections with the fact that the resistors are parallel to each other. Let me show you an example. Let's say we have this connection. Say 3 and 6. And then we have this connection. Three and 6. Notice both of these circuits, the resistors are drawn parallel to each other. So that's tempting to want to say, because they're parallel to each other, they must be connected in parallel. But this is not true. A parallel connection does not have anything to do with how the resistors are drawn parallel to each other. Okay, it's a misnomer. Let's look at this first example. The current comes in, and it reaches a point where there's a choice to be made. It could either go up or it could go down. But then after that choice, they come back together and keep on going. That's parallel. The current can flow in one branch or the other branch, but it doesn't have to go through both. In the second example, the current comes in, it hits the first one, keeps on going, and then has to hit the second one. There's no choice there. So this one's series, and this one's parallel. In fact, because these are just drawings, they're just lines, I could redraw this second one to make it a lot more clear that it's series. And all I'm going to do is I'm going to take this resistor and I'm going to pulling the wire so that it's up here now. Put it up here. And so what we have is, here's the 3, here's the 6, and now we have all that wire I just stretched. So I pulled it from the bottom, pulled it all the way up to the top, kept everything connected. I didn't disconnect anything. I just lengthened that bottom wire. And so now this is the 3, and this is the 6, and this is the 10. These are the same circuit. They're exactly the same. It's just that they're drawn differently. I decided, when I drew it the first time, to draw it such that the resistor looks like it's on the bottom, and the second time it looks like it's on the top. But if you follow what the current sees as it flows, they're identical. The current leaves the voltage, it hits a 3, keeps going, it hits a 6. And it keeps going and gets back. It doesn't matter if you're in the top drawing or the bottom drawing, it's the same thing. So, let this be a lesson. The fact that they're connected in parallel has nothing to do with the fact that they're drawn parallel to each other. Okay? The parallel connection has to do with when the current reaches a certain point, that current can either go in one branch or another. There's an option for how the current wants to flow. Okay? Now, one way of doing this that I see a lot of people like is when you're given a circuit, you write down or you draw what's called nodes for every element. So I'll do it for these. Here's a voltage source on this left one. So there's a node here and a node here. They're just little dots or circles you draw at the end, either end of every element. Okay? This top resistor, the 3, here's a node and here's a node. This bottom resistor of 6, here's a node and here's a node. So those are the nodes for him. Let's do these other two circuits. Here are the nodes for the 10. Here are the nodes for the 3. And here are the nodes for the 6. Same for the bottom one. Here's the 10. Here's the 3. And here's the 6. Okay? All I did was put a dot on either end of every single element in the circuit. Now the rule says this. Resistors are parallel if they share 2 nodes in common. Resistors are in series if they share only 1. So let's look at these two examples to see how that works. Look at the series one. Let's look at this bottom one first. The 3 and the 6. How many nodes are common to both? Well, this node right here is on the 3 and it's on the 6. But this guy for the 6 is not common with the 3. It's different. And this node for the 3 is not common with the 6. It's only with the 3. So the only node that's common to both is the one in the middle. So they share one node. They must be series. What about the top? The top drawing. Well, here's the 3s, and here's the 6. However, notice this one here, these two on the right. There's nothing between those two nodes. There's a node on the top right, there's a node on the bottom right, and in between them is just wire. There's not another resistor, there's not a voltage source, there's not a branch, it's just wire. So really, this is all one big node, called a supernode if you want. So it's really just one node sitting there. It's not really two. And once you can see that, then you notice the 3 and the 6 share this big node in common, but their other nodes are not shared. It's just with them. So again, the 3 and the 6 are series. Now let's look at the parallel. How is this different? Look at the 3 and the 6. Well, again, the 3 has this guy, and the 6 has this guy and this guy. But, again, we notice that between the left side nodes for the 3 and the 6, there's just wires sitting here. So really, this is one big node sitting here like this. And on the right, this guy and this guy, just wire between them, so they're really just one big node as well. And now we look, the node on the left for the 3 is the same as the node on the left for the 6, as well as the right node for the 3 and the right node for the 6, they're the same. So the 3 and the 6 share two nodes, this one and this one. They share two nodes in common, so they must be parallel. So that's another way of trying to look at the circuit and figure out if this is series or parallel. How many nodes do they share? If they only share one, that's series. If they share both, it's parallel. Once you've got that, at the end of the day, all you're doing is figuring out if it's series, I add up the resistors together. If they're parallel, I add up the reciprocals. So here's an example. Take this. Circuit. Let's say 8, 3, and 6. And I want to know, find the total resistance. Well, in order to find the total resistance, I need to know what resistors are in series and what resistors are in parallel. An easy way to do this is to look at the nodes. Here's the node for 8. Here's the node for 3. Here's the node for 6. And we say, okay, notice the 3 and the 6 share this node in common, and the 3 and the 6 share this node in common. So this tells me the 3 must be parallel to the 6. So I could take 1 over R parallel is 1 over 3 plus 1 over 6. 1 over 3 plus 1 over 6. 1 over 3 becomes 2 over 6. 2 over 6 plus 1 over 6 is 3 over 6. But that's 1 over R parallel, so R parallel must be 6 over 3, which is 2. Now what about that 8? We didn't include the 8 here. 8 was left alone because we can't incorporate him into the parallel because he's not parallel. If 8's left side node was shared by the 3 and the 6, then he would also be parallel with him. But it's not. That 8 is sitting out there by himself. So you had to leave him by himself. So what do we do? Well, what we do is what's called creating an equivalent circuit. We have the main circuit. We just calculated this 3 and the 6 parallel piece has a total resistance of 2. So now we can redraw this circuit. The 8 is still there. But now instead of 3 and 6 being parallel, let's make just one single resistor whose total resistance is that parallel piece. Here's the 8 we didn't touch, and here's the 10 for the voltage. Okay, so all we did was we took this parallel piece here, calculated the equivalent resistance of that piece, and then created a single resistor with that equivalent resistance. This is called an equivalent circuit. It means it works the same way as the other, but it's more simple. All right, now that I have this, I do the same thing. What are the nodes? Here's the nodes for the 8. Here's the nodes for the 2. How many nodes does the 8 and the 2 share? They share this single node in common, so they must be series. So our series is 8 plus 2, which is 10. I now know the total resistance of my circuit is 10. How do I know that's the total? Well, I just combined the 8 and the 2 into 1. So again, I have an equivalent circuit with just one single resistor sitting there. And what's his equivalent resistance? Well, the 8 and the 2 added to 10, so he's 10. So now this original circuit we started with is basically the same as this simplified circuit with just one single resistor. What's his resistance? 10. Thus, the total resistance of my complicated circuit must be 10. So, this is what we're doing for this lesson. We have a circuit, multiple resistors in the circuit connected both parallel and series combination. I break down those resistors until I get a total resistance. Once I have a total resistance, I can then use Ohm's law to find the total current. So, I hope this is useful. I will be posting another video with example problems, calculating total resistances and stuff like that. Look out for the practice problems on Canvas. Be sure to start working on them. This is the fundamental thing you need to understand how to do for the rest of the semester. You must be able to see what's series, what's parallel, be able to combine things as they are in series and parallel, breaking them down to smaller and smaller pieces, smaller equivalent circuits, until you have a total resistance at the end. Once you have that, you can calculate your total current. So, hope this makes sense. As I said, expect some example problems video. Look out for the practice problems on Canvas, and the next homework, I'll let you know when it's posted. But until next time.